Hey everyone, welcome to this explainer. Today we're building a complete computer vision pipeline from absolute scratch. If you've spent any time at all in the machine learning trenches, you already know image classification is the bedrock of the field. It's the foundational skill that transfers to literally every other computer vision task out there. Whether you're building an object detection system, classifying regions, or a semantic segmentation model looking at individual pixels, getting classification right, that's where it all begins. So let's dive into how this pipeline is actually built, not just in theory, but in real-world practice. Here is our architectural blueprint for today. First, we'll uncover those sneaky, silent classification bugs. Second, mastering data and augmentation. Third, understanding logits and loss. Fourth, the 5 training invariants. And finally, evaluating beyond just aggregate accuracy. All right, let's jump right into section 1, the silent classification bugs. It's all about the plumbing versus the brain. We've got to shatter a massive misconception right out of the gate here. When a model fails, it's super tempting to blame the architecture, right? The neural network's brain. But in reality, most machine learning bugs do not live in the model itself. They live in the unglamorous plumbing. To put that into perspective, look at this. If you have a convolutional neural network that is perfectly capable of hitting 93% accuracy on a dataset like CFAR10, it'll commonly score only 70 to 75% simply because of a broken setup. And honestly, here's the terrifying part. These bugs are completely invisible. They will never throw an error code, your script will run, it'll happily utilize your GPU, and it'll spit out a saved model, completely masking the fact that it's deeply flawed. So you've really got to ask yourself, where do these silent killers actually hide? How on earth can a model lose nearly 20% of its potential accuracy without Python or PyTorch yelling at you? Well, the scariest aspect is that your training loss curve often looks completely plausible the entire time. It goes down nice and smooth, totally tricking you into thinking everything is perfectly fine. Let's trace where things actually go wrong across the anatomy of your pipeline. Think about it. You load the dataset, apply random augmentations, normalize the pixels, pass it all through your model, and calculate the loss. A silent bug can live in literally every single line of this loop without ever crashing your code. A broken normalization, maybe an unshuffled dataset, or an augmentation that accidentally distorts the labels. Any single one of these will just flatten your learning curve quietly and completely. Moving right along to section 2, mastering data and augmentation, or as I like to call it, teaching invariances. You see, a convolutional neural network actually only has one built-in bias, and that's for translation, thanks to weight sharing. It doesn't inherently know that a cropped, flipped, or color-shifted dog is still a dog. We have to explicitly teach it those invariances by showing it altered pixels while telling it, hey, this still has the exact same label. To really wrap our heads around how a CNN views this data, we've got to talk about the receptive field. A neuron deep inside your network does not look at the whole image at once. It only sees the specific patch of pixels that fed into it from the layers below. By stacking multiple layers with small kernels, like simple 3x3 grids, the network cheaply builds a very large field of view. It's a pretty brilliant way to understand the whole image without relying on one giant, super computationally expensive filter. Now, we can definitely push data augmentation to the next level. Standard transforms like a basic crop or a flip change the pixels but keep the labels one hot. That means the image is still 100% a dog or 100% a cat. But advanced techniques like Mixup and Cutmix, they completely break that rule. They actually interpolate both the pixels and the labels. Mixup literally blends 2 images together, while Cutmix pastes a random rectangle of one image into another and then area weights those labels. This is huge because it stops the model from just memorizing spiky, one-hot targets and forces it to actually understand the complex space between classes. But listen, no matter what crazy augmentations you try, you absolutely must obey the golden rule. Preserve the label. Think about it. If you rotate a number 6 too far, it becomes a 9. Boom, you just broke the rule. Also, a quick pro tip for you. When cropping images, using reflect padding is significantly better than zero padding. Zero padding creates these artificial black borders around your images, and let me tell you, neural networks are incredibly lazy. Your model will actually learn to use those black borders as a cheating signal, which is completely useless for real-world performance. All right, on to section 3, understanding logits and lusts. Welcome to the Softmax Trap. Moving from the data flowing in to the predictions flowing out, let's get our terms straight. A classifier produces a set of raw numbers for each image, one for each possible class. We call these logits. Cross-entropy is the loss function that measures the negative log probability of the correct class. Now here is the absolute crucial detail. Frameworks like PyTorch actually fuse the softmax function, which turns those raw logits into probabilities, and the negative log likelihood directly into one single numerically stable operation under the hood. And because of that under-the-hood fusion, there is a bold, unbreakable rule you must follow. Applying softmax yourself before the loss function is almost always a bug. I know, it is incredibly tempting to want to manually convert your model's raw logits into neat, readable probabilities before passing them to the loss function. It just feels right, but you have got to resist that urge. So let's look at exactly what happens mathematically if you make that mistake. If you apply softmax yourself, and then the cross-entropy function applies softmax again, you are literally computing the softmax of a softmax. This squashes everything into nearly uniform probabilities. The result? You generate totally useless, meaningless gradients, and your model's accuracy will drop by exactly 1 divided by the number of classes. It's this silent little math error that will completely kneecap your model without throwing a single warning. Let's hit Section 4, the 5 training invariants. Consider this your definitive loop checklist. Okay, so we fixed the data and we fixed the loss. Now let's look at the training loop itself. This is the engine of your pipeline, and here is the checklist of 5 non-negotiable invariants to keep it from blowing up. 1. Always explicitly set model.train before training and model.eval before evaluating, just to ensure things like dropout behave correctly. 2. Call optimizer.zeroGrad once per step. Skipping this accumulates gradients and makes your learning rate look wildly unstable. 3. Always use .item when accumulating metrics, otherwise you're keeping the entire computational graph alive in the background and you will absolutely run out of memory. 4. Use the torch.nograd decorator during evaluation to save memory and time. And 5. Always run your argmax against your raw logits, not a softmax output. It gives you the exact same result, but saves you a whole computational operation. Finally, we arrive at Section 5, evaluating beyond aggregate accuracy. It's time to find the truth. All right, you've trained your model flawlessly using all the best practices we just talked about. Now it's time to test it. But we need to attack a deeply flawed concept that misleads developers every single day: aggregate accuracy. Imagine you evaluate your model and it spits out a shiny 92% accuracy score. You might be tempted to pop the champagne, right? But I'm here to tell you that this 92% can easily be a complete lie. Think about it. What if your dataset has 10,000 images and 9,000 of them belong to class 0? Your model could just blindly guess class 0 for every single image it ever sees, and it would technically score a 90% aggregate accuracy while learning absolutely nothing. This right here is exactly why we absolutely must look at a confusion matrix to see what is actually happening inside your model's brain. In this matrix, the rows are the true classes and the columns are your model's predictions. See that diagonal line running right down the middle? Those are your correct predictions, but the off diagonals, those are the most important part. That is where your model's actual failures live. If you see a big cluster of numbers in an off diagonal, you instantly know your model is confusing those two specific classes. So the big takeaway here is that aggregate accuracy hides severe data imbalance. True evaluation requires you to look at per-class precision and recall. By using confusion matrices, you can diagnose exactly where your dataset is falling short. It tells you precisely where you need targeted data collection or maybe some specialized augmentations. Doing this turns evaluation from a vanity metric into a real, actionable diagnostic tool. We've definitely covered a lot of ground today in this explainer, from the hidden dangers of the Softmax Trap to the absolute necessity of rigorous evaluation. Mastering this unglamorous plumbing, the dataset loops, the augmentations, the proper loss calculations, is hands down the single most transferable skill in all of computer vision. So as you go back to your code editor today, I want to leave you with this final provocative question. Which silent bug is living in your plumbing right now?